Good afternoon, everyone. This is our fourth topic. 44. This is my 44th for Real Analysis Math 305. I am your instructor for this afternoon. You're still me, A. Bustamante. Lesson 3, Mathematics from Main Campus. So, our topic for this afternoon is all about infinite intervals, which found in section 10.3 infinite intervals. In the preceding two sections, we have discussed the integration of functions, defined and bounded closed intervals a b. However, in applications, we often want to integrate functions defined on unbounded closed intervals such as a positive infinity, negative infinity, b, or negative infinity, positive infinity. In calculus, the standard approach is to define an integral over a positive infinity as a limit, like this. Integral a to positive infinity of f equal to limit of integral a to y f as y approaches positive infinity, and to define integrals over the other infinite intervals similarly. In this section, we will treat the generalized Riemann integrable and Lebesgue integrable function defined on infinite intervals. In defining the generalized Riemann integral of a function of f on an interval a positive infinity, we will adopt a somewhat different procedure from that in calculus. We note that if q is equal to x sub 0, x sub 1, t sub 1, dot dot dot, x sub n minus 1, x sub n, t sub n, x sub n, interval x sub n, positive infinity, t sub n plus 1 is a tag partition of an interval a positive infinity. Then x sub 0 equal to a and x sub n plus 1 is equal to positive infinity, and the Riemann sum corresponding to q has the form. For 1, f of t sub 1 multiplied by x sub 1 minus x sub 0 plus dot 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 plus f of t sub n multiplied by x sub n minus x sub n minus 1 plus f of t sub n plus 1 multiplied by x positive infinity minus x sub n. Since the final term of f of function f is f of the t sub n plus 1 multiplied by positive infinity minus x sub n in 1 is not meaningful. We wish to suppress this term. We can do this in two different ways. 1. Define the Riemann sum to contain only the first n terms. Or 2. Have a procedure that will enable us to deal with the symbols positive, negative, infinity in calculations in a such way that we eliminate the final term in 1. We choose to adopt method 1 instead of dealing with partitions of an interval a positive infinity into a finite number of non-overlapping intervals, one of which must necessarily have infinite length. We deal with certain subpartitions of an interval a positive infinity, which are finite collections of non-overlapping intervals of finite length whose union is properly contained in an interval a positive infinity. We define a gauge on an interval a positive infinity to be an ordered pair consisting of a strictly positive function delta defined on a positive on an interval a positive and positive infinity and a number b to the power of asterisk is greater than 0 when we say that the tag sub partition is equal to an interval x sub 0, x sub 1, t sub 1 dot 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 x sub n minus 1, x sub n, t sub n is delta and d to the power of asterisk we will find. We mean that 2 is an interval of a positive infinity union I is equal to 1 and n is n. X an interval x sub I minus 1 and x sub I union x sub n and positive infinity. That 3 x sub I minus 1 and x sub I subset is a subset of t sub I minus delta of t sub I plus delta of t sub I for I is 1 dot 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 n. And that for x sub n positive infinity is a subset of 1 divides d to the power of asterisk positive infinity or equivalency that 1 over d is less than or equal to x sub n. Note that ordinarily we will consider a gauge on an interval a and positive infinity to be a strictly positive function delta with domain of an interval a and positive infinity equal to a and positive infinity union of positive infinity, where delta of positive infinity is equal to d, which definition 10.3.1 definition. So 10.3.1 definition, a function f is a and positive infinity to real number is said to be generalized Riemann integrable if there exists a is an element of a real number such that for every epsilon is greater than 0 there exists a gauge, a delta sub e on an interval a and positive infinity, such that if p is in any delta sub e, find tag subpartition of a and positive infinity, then s of f partition minus a is less than or equal to epsilon. In this case, we write f is an element or belongs to r to the power of asterisk, which we can say a set of non-zero real numbers a and positive infinity, and integral a to positive infinity f equal to a. A function f is a and positive infinity to r. Real number is said to be Lebesgue integrable if both f and absolute f belongs to a set of non-zero real numbers a, positive infinity. In this case, we can write f of f is belongs to L of a positive infinity. Of particular importance is the version of Hicks theorem for functions in a set of non-zero real numbers a positive infinity. Other results for functions in L a positive infinity will be given in the exercises. 10.3.2 Hicks theorem. If f is a and positive infinity to real numbers, then f belongs to belongs to a set of non-negative real numbers a and positive infinity if and only if for every y it belongs to a positive infinity. The restriction of f to an interval a y belongs to a set of non-zero real numbers interval a y, and the limit of integral a to y f equal to a belongs to or an element of a real numbers and y as approaches a positive infinity. In this case, integral a to positive infinity f equal to a. The idea of a proof of Hicks theorem is as before. The details are given in MTI. The generalized Riemann integral on the unbounded interval a positive infinity has the same properties as this integral on a bounded interval of a and b that were demonstrated in section 10.1. They can be obtained by either modifying the proofs given there or by using Hicks theorem. We will give two examples. We have an examples for letter A. If f g belongs or an element of a set of non-negative real numbers of an integral a positive infinity, then f plus g of an element of a set of a non-negative real numbers of a and positive infinity, and integral a to positive infinity of f plus g equal to integral a to positive infinity f plus integral a to positive infinity g. If epsilon is greater than 0 is given, let by the delta of f be a gauge on an interval a and positive infinity such that if partition is delta of f from the right, find then s of f partition minus integral a to positive infinity f is less than or equal to epsilon over 2, and there exists a gauge of delta sub g such that if a partition is delta sub g from the left, find then it is has a absolute of s of g partition minus interval a to positive infinity g of less than or equal to epsilon over 2. Now let delta sub epsilon of t equal to minimum of delta sub f of t and delta sub g of t for t is an element of a and positive infinity, and argue as in the proof of 10.1.5. Let f a and positive infinity is a real number, and let c is an element of a and positive infinity. Then f is an element of a set of a non-negative a non-zero is a set of a non-zero real numbers. An interval of a and positive infinity if and only if its restrictions to a part interval a and c and positive infinity are integrable. In this case, integral a to positive infinity f equal to integral a to c f plus integral c to positive infinity f. We will prove using Hicks theorem by the hypothesis the restriction of f to an interval c and positive infinity is integrable. Therefore, Hicks theorem implies that for every y is an element of c and positive infinity, the restriction of y to an interval c and y is an integrable, and that integral c to positive infinity f equal to limit of integral c to y f as y approaches to positive infinity. If we apply the additivity theorem 10.1.8 to the interval of a and y equal to an interval a and c union of an interval c and y, we conclude that the restriction of f to an interval a and y is integrable, and that integral a to y f equal to integral a to c f plus integral c to y f. Whence it follows that limit of integral a to y f as y approaches to positive infinity is equal to integral a to c f plus limit of integral c to y f as y approaches to positive infinity equal to integral of a to c f plus integral c to positive infinity f. Another applications of Hicks theorem establishes for number 6, this one. 10.3.4, example A, let A is greater than 1 and let f sub a of x equal to 1 over x to the power of a for raised to the power of a for x is an element of 1 and positive infinity. We will show that f sub a is an element of a set of non-zero real numbers 1 and positive infinity. Indeed, if y is an element of 1 and positive infinity, then the restrictions of f sub a to 1y is continuous and therefore belongs to a set of non-zero real numbers 1 and y. Moreover, we have integral 1 to y 1 over x raised to the power of a dx equal to 1 all over 1 minus a multiplied by x to the power of 1 minus a absolutely start from 1 to y equal to 1 over a minus 1 multiplied by the interval of 1 minus 1 over y to the power of a minus 1. But since the last term tends to 1, tends to 1 over a minus 1 as y approaches to positive infinity. Hicks' theorem implies that f sub a is an element of a set of a non-zero real numbers 1 and positive infinity, and that integral 1 to positive infinity 1 over x sub x to the power of a dx equal to 1 over a minus 1 when a is greater than 1. Let summation of ak k is equal to 1 and to positive infinity be a series of real numbers that converges to a is an element of a real number. We'll construct a functions s is an element of a set of non-zero real numbers 0, 0 and positive infinity such that integral 0 to positive infinity s equal to a summation of k equal to 1 to positive infinity ak equal to a. 10.3.5 Fundamental Theorem. Suppose that E is a countable subset of A and positive infinity, and that f A and positive infinity is our real numbers are such that f is continuous on an interval a and positive infinity, and limit of f of x exists as x approaches to positive infinity. Letter B. F prime of x is equal to f of x for all x is an element of a and positive infinity. X is not an element or does not belongs to E. Then f belongs to a non-zero real numbers a and positive infinity, and integral a to positive infinity f equal to limit f of x minus f of a as x approaches positive infinity. Proof: if y is any number in an interval a and positive infinity, we can apply the fundamental theorem 10.1.9 to the interval of a and y to conclude the function f belongs to a set of a non-zero real numbers of an interval a and y, and integral a to y f equal to f of y equal to f of a. Letting y approaches to positive infinity, we conclude that from Hicks' theorem that the function f is an element of a set non-zero real numbers a and positive infinity, and that equation number 7 holds. Integrals over negative infinity and b. We now discuss integration over closed intervals that are unbounded. Below, let b is an element of real numbers and g is interval with interval of negative infinity, and b to a real number be a function that is to be integrated over the infinite interval of negative infinity and b. By a gauge on negative infinity and b, we mean an ordered pair consisting of a number d is a greater than 0 and a strictly positive function delta on an interval negative infinity and b. We say that a tag partition is x sub 0, x sub 1, t sub 1, x sub 1, x sub 2, t sub 2, x sub n minus 1, b, t sub n of negative infinity b is d delta. Find in the case that negative infinity and b equal to negative infinity and x sub 0 union of a u starts with I equal to 1 and ends with n, and with interval of x sub I minus 1 and x sub I, that an interval x sub I minus 1 x sub I is a subset of ti minus delta of ti t sub I rather t sub I plus delta sub t sub I for I is equal to 1 dot dot dot, and that is negative infinity, and x sub 0 is a subset of negative infinity and negative 1 over d, or equivalently that x sub 0 is less than or equal to 0 is equal to 1 over d. Ordinarily, we consider a gauge on a negative infinite and b to be a strictly positive function delta with domain of negative infinity and b equal to negative infinity union of negative infinity and b, where delta of negative infinity is equal to d. Here the Riemann sum of h Riemann of h of partition of s h partition of equal to summation I equal to 1 and ends to n, h of t sub I multiplied by x sub I minus x sub I minus 1. Finally, we say that h is an h is negative infinity and positive infinity are real numbers, is generalized Riemann integrable if there exists C is an element of a real number, such that for every epsilon is greater than 0 there exists a gauge of delta sub epsilon on an interval negative infinity and positive infinity, such that if partition is any delta sub epsilon, find subpartition of interval negative infinity and positive infinity, then absolute S of h partition minus c less than or equal to epsilon. In this case, we write h is an element or belongs to a set of a non-zero real numbers, negative infinity and positive infinity, and integral negative infinity to positive infinity h equal to c. Similarly, a function h is a partition of negative infinity, positive infinity is a real number, is said to be a Lebesgue integrable if both h and absolute h is belongs to a set of a non-zero real numbers of negative infinity and positive infinity. In this case, we write h is an element or belongs to L of negative infinity and positive infinity. In view of its importance, we will state the version of Hicks theorem, and that is valid for the integral over negative infinity and positive infinity. 10.3.6 Hicks theorem. If h, a partition of h, is negative infinity and positive infinity is a real number, then h belongs to a set of non-zero real numbers and of negative infinity and positive infinity if and only if for every beta is less than 2 y in an interval of negative infinity and positive infinity. The restriction of h to an interval beta and y is in a set of non-zero real numbers interval b and beta and y, and limit of integral beta to y h equal to c, it belongs to a real number which b beta is an approaches to negative infinity and y is approaches to positive infinity. In this case, integral of negative infinity to positive infinity h is equal to c. As before, most of the theorems valid for the finite interval of a and b remain true. They are proved as before or by using Hicks' theorem. We also state the first form of the fundamental theorem for this case. So, 10.3.7 Fundamental theorem. Suppose that E is a countable subset of a negative infinity and positive infinity, that H partition of H negative infinity and positive infinity is a real number. Satisfy A. H is continuous on an interval negative infinity and positive infinity, and the limits of h of x exists which x is approaches to positive negative infinity. B. H prime of x is equal to h of x for all x belongs to an interval in negative infinity and positive infinity. X does not belongs to E. Then H belongs to a set of a non-zero real numbers of an interval negative infinity and positive infinity, and integral negative infinity to positive infinity. H is equal to limit of h of x minus limit of x h of y, here which x approaches to positive infinity, and limit of x h of y where y approaches to negative infinity. 10.3.8 examples. A, let h of x partition of 1 over x squared plus 1 for x belongs to an interval negative infinity and positive infinity. If we let partition of h of x is equal to arctan x, then h prime of x is equal to h of x for all x belongs to an interval negative infinity and positive infinity. Further, we have limit h of x equal to 1/2 of pi, and where x approaches as positive infinity, and limit h of x equal to negative 1/2 of pi, where x approaches as negative infinity. Therefore, it follows that integral negative infinity to positive infinity 1 over x squared plus 1 dx is equal to 1 over 2 pi minus 2 negative 1 over 2 pi equal to pi. Let k let k of x equal to x absolute of x e to the power of x, and negative x is to the power of 2 for x belongs to an interval negative infinity and positive infinity. If we let k of x equal to 1 over 2 multiplied by 1 minus e to the power of x squared for x is greater than or equal to 0, and k of x is equal to negative 1 over 2 multiplied by 1 minus e to the power of raised to the power of raised to the power of x squared rather. For x is less than 0, then it is seen that k is continuous on an interval of negative infinity and positive infinity, and that k prime x equal to k of x for all x is not equal 0, is not equal to 0. Further, limit k of x equal to 1 over 2 as x approaches approaches to positive infinity, and limit k of x equal to negative 1 over 2 as x is approaches as negative infinity. Therefore, it follows that integral of negative infinity to positive infinity absolute x e to the raised to the power of x negative raised to the power of negative x squared dx equal to 1/2 minus the quantity of negative of 1/2 equals to 1. And that's all. Thank you for listening. Thank you, class. Goodbye.